All right, so inverses of exponential functions. We're going to do both parts, hopefully, is our goal for today. So up first is part one. And in part one, we are talking about the general form of a log function. And so the general form of our log function is going to be, I don't know why my pen keeps doing this. Is f of x equals a log base b of x. Okay, with the base of b. Okay, and b can be anything that's greater than 0. B cannot equal 1, and your a cannot equal 0. Okay, so we're going to dive in and talk about the function, what it looks like. And again, this is meant to feel like there's a line. It finally has appeared. That's what I wanted to. Okay, so first we're going to start off with our parent function. The parent function for a log function is typically letting b equal 2. Does that make sense? So for our parent function, we're label this as our PF, our parent function. If we were to substitute these values in, what do we get? So f of x equals 2 to the x. So if I let x equal -2, that equals 1/4. If I let x equal -1, that equals 1/2. If I let x equal, is just going to equal 1. It's at the bottom of the basket. I asked y'all to make sure you're good with them. They're at the bottom of the basket. It's going to equal 2, and then 2 squared is going to equal 4. Okay, so those are our y values of our parent function. Now we're gonna go ahead and graph it, kind of just sketch it out a little bit to the best of our ability, and go from there. For graphing purposes, I'm going to encourage us to kind of count out by ones up to 4. So this will be -1, -2, -3, -4. And then on here, I'm going to do it by halves more so. So this will be a half. And this will be 1. I needed 4, didn't I? Did. Oh, well, you'll get the point. Okay, so when we graph our points, it says at -2, you're at 1/4. So halfway here, right? And that's not -2, Sean. Go over 1. Okay, -2, you're at 1/4. At -1, we're at 1/2. And at 0, we're at 1. So we all remember our exponential function looking like this, right? That is pretty curvaceous. So put that out. I'm just saying. That's legit pretty good. I know we're gonna mess up here in a minute, but I just want y'all to acknowledge that that was pretty good for me. All right. Now we're gonna talk about the inverse. Okay. Remember when we graph an inverse graphically, we can tell their inverses if they are reflected over the y equals x line. Remember that? So it's that diagonal line that divides it into 2 equal parts. That's our y equals x line, right? So now we're going to do our inverse. What? Yes. Origin? Yes. It has to go through. Okay. So when we're doing our inverse, that means we're doing what with our x's and y's? Switching. So 1/4 is no longer my y, but it is my x. So we have 1/4 and -2. We have 1/2 and -1. We have 1 and 0. We have 2 and 1, and we have 4 and 2. Okay, so what this is saying that the log base 2 of 1/4 is -2. this is saying that the log base 2 of 1/2 is -1. This is saying the log base 2 of 1 equals 0. The log base 2 of 2 equals 1. And the log, okay. And then this is saying the log base 2 of 4 is 2. Okay. So if I solve something exponentially, then I automatically can know the answer of its log, right? All right, so now we're going to graph, and I'm going to keep hope alive on my graph still. So I'm going to go, this is going to be -1/2. This is going to be -1. And then I'm going to 1, 2, 3, 4. Okay, so now I'm at a quarter, and a quarter is -2. But I don't have room to be on there. So my -2 is going to be off a little bit. It's going to be down here. You know what? I can be smart. I can make it longer. Duh. Not enough room where? Still not enough. It's all at the bottom. It's down here. It's not going to work. Okay. So here's my quarter. Now I'm going to go to a half, and a half is at, where's a half at? At -1. So at a half, I'm at -1. Where's -1 at? I mean, where we at? 1. 1 is at 0. And then 2 is at, I didn't draw a very good line. Dang it, Bob. I should just count it the same. I don't know why my graph isn't cooperating with me.
That means it's like way up there. Mine makes sense.
It's my y equals x line. I forgot that it had to be tilted because I'm not counting by the same. There we go. I'll fix it. I'll draw it in there in a second. It's on me and my 2x. There we go. All right, so here I go doing my very best. I'm hoping for the same herbaceous experience here. I shall keep hope alive.
Oh,
it didn't work. It didn't work. It didn't work.
You could just gone with
Because I didn't count by the same thing on each axis,
you should have.
and I should have for it to be as.
Look at my graph.
Okay, okay.
I'm passing it to you. It's just a little bit.
I believe you. Okay.
No, just look.
I don't want to.
Look at it.
I don't want to. I don't want to. My scale factor is horrible. I should have known better as a person. These are symmetrical. I should have known that I should have chose the better scale factor. I take my responsibility. I'm not looking at yours. We're just gonna look at it in a different way. I don't need you to rub it in my face that I struggled in that moment. All right. It's cool though. I can do it. I got it. What was it? 2? What are you doing? 2. I know I typed it 2. And X. Oh, you can't type X on with the keyboard. Lesson learned. All right. So, I just want to know if I make my settings how mine were. From -5 to +5, counting by ones. Right? And then, should I just put in the same dimensions? Yeah. -5 to 5, counting by ones.
Wait, where did you go for that? Wait, is that?
This is what my graph was supposed to look like.
I'm wondering why you did the
Because I thought it would save me time in the fraction in the drawing, like trying not to estimate, being hopeful. But if we just count by scales, ta-da! Are they inverses? Yes, they are. Just for giggles. What happens if I do change my y's? And my lowest y is -1.5. And my highest y is 1. And my scale factor is 0.5. Let's just see. Basically what I did. Yes, the first one. Is that it's what I had. Y'all try to doubt me.
struggling though.
I knew I drew it right.
I drew it the way you
If
drew
it, I knew I drew it right. I knew I did. I just shouldn't have did the y equals x where I put it. Because it went to look. But yes, because I'm zoomed in on the y scale. That's why. But yeah. I did use different colors. Yeah. My colors, I still use blue and red. They're not aside, whatever. You know what we did. All right. So the moral of the story here is that exponentials and logs of the same base are inverses. Only 2 people said that. So let's try that again. The moral of the story here is that exponential and logs of the same bases are. Yay. Now you'll remember. Okay. All right. Yes, we're going to pretend that you are. Okay. Now we're going to talk about just analyzing the function. So we're going to draw the actual log base 2x here and talk about all of its properties. Okay. So for log base 2, we started off at, we're going to do 1. And then 2 was 1. And then we went all the way over to, we can go over to 8.
How do you know, like, how did you know, like, in your head what log base 2 the 2 is? Because she's heard.
We wrote it down. We did it right here.
Oh.
No, we wrote it right here.
Oh, but like you didn't know that.
I'll tell you why I do in a second. Yeah. But yeah, no, we wrote it right there. So I can tell you why I knew it was 8. So this is asking you when you're graphing log, you're asking yourself 2 to the what power, right? But it's the reverse of it. What's going to give me 8? Well, that's going to be 2 to the 3rd power. What would give me 16? That would be 2 to the 4th power. Okay. So that's how log works. Log is saying, here's my answer. What power makes that answer for that base? Does that make sense? Okay. So if my answer is 1, 2 to what power makes 1? 0, which is why we're at the 0, right? If my answer is 2, 2 to the what power makes 2? 2 to the 1. Okay. If my answer is 4, 2 to the what power makes that? 2 to the 2. Okay. The log is the inverse. You're asking the opposite question of an exponential. Okay. With the exponential, you're saying 2 to the 2nd power is what? You're looking for your answer, right? With log, you're looking for what gave you that argument. Okay. All right. So as you look here, it keeps going and going and going. So we already know that the halves go down. It just keeps getting smaller and smaller. Just don't want me to be great. I can't. I'm concentrating real hard, but it's okay. Oh. You get it. You get it. It's easier on paper, and I'm way better on paper. Okay. Yes, we're in paper. We're going to write out our table. So our table of values that we have are, so for 2 to the x, these are going to always be your table of values that you would use as far as transformations, referring to points, and things like that. We know that 1 is 0. We know that 2 is 1. We know that 4 is 2, and we know that 8 is 3. So again, this is telling me 2 to the 0 power is 1. 2 to the 1 power is 2. 2 to the 2 second power is 4. 2 to the third power is 8. All right, domain. What is the domain of this function? 0 to infinity. The reason why it's 0 to infinity is that there is an asymptote here. Okay, that's because, well, 2 to any power make a negative number. So we have a restriction here. So our domain is from 0 to infinity, meaning that x has to be greater than 0. Nope, because there's an asymptote. So if I have an asymptote here, my range, what is my range though? All real numbers, infinite possibility. Okay, we're going to talk about our end behavior, our limits. So the limit as x goes to positive infinity, what is y doing? Y is going to infinity. I didn't mean to write y because it's already written for us as f of x. F of x is going to infinity. Okay, as the limit as x goes to 0, what is it doing? Y is doing what? Y is heading to negative infinity. Okay, the reason why it's heading to negative infinity is because there's a what? An asymptote. We have a vertical asymptote at x equals 0. Do I have any intercepts? Yes. We have an x-intercept at 1, 0. And what type of concavity is this? Concave down. Good job. And the reason being is because the rate of change, can I write R? Are we okay? All right. Rate of change. The rate of change is decreasing. All right, cool. So now these overall rules are going to be the same for all log functions. What changes are going to be your table values. So if my log base 2 is now 3, these are going to be the same values, right? But all of the attributes, characteristics stay the same. Got it? The attributes are going to stay the same regardless if your B changes. Okay? Now, with that being said to you, I lied. Can someone tell me an example of why it changes? What's going to change? What's going to be the thing that changes here? The domain's not going to change. The range is going to change.
Is it going to be a compression?
Stretched out.
Okay. What happens if you have a half power?
Is it gonna switch? Is the X is gonna
If I have a half power of a fraction, of an exponent, right? 2 to the half, right? So that means I'm taking the square root of 2. So instead of growing, it's getting smaller, right? So what's going to happen here with the inverse? It's going to do the same thing. It's now going to have to also get smaller. So let's make a table and see what happens. Are y'all ready? So we have X, Y. All right. So if we're going backwards, we're asking ourselves, yeah, we're seeing some X values. So our values are still going to be, what was it? Yeah. 1, 2, 4, and 8. Okay. But what do you think can happen to these values as 1, 2, 4, and 8? They're changing. But how do you think they change? Mhm. What would make a power negative? Like, how do I make a power into a fraction? Then an exponent into a result to a fraction. The power what? The power has to be negative, right? So what's going to happen to all of their y values? They're going to be negative because otherwise will I produce a fraction? But now everything is going to be negative. Well, except 0. 0 is going to be what? 0. Yeah, you can write that if you want. -1. Y'all had to say his name. You couldn't just let it have been a situation that happened to a student.
The 1/2 is the power?
The 1/2 is what you're resulting as. We're gonna inverse. Mhm. We have enough to do 8. I mean, technically you could do 16 too. If you want to do -4. Your asymptote is still at 0, but instead of it being what changes? So your concavity changed, right? Your concavity is no longer down, it's up. And that's 1. Nope, I knew I was going to put it in the wrong spot. The level of concentration for me to graph is really sad. That's how you know I had no artistic abilities as a kid. Like, I had no hope. Okay, ooh. I'm not going to finish it strong. Okay, you get it. That took a lot out of me. Again, it's the board. I'm better at paper. All right. So again, our domain here is. And why am I not using a bracket? An asymptote. My range. All real numbers. This time, as x goes to positive infinity, what are your y's heading to? Negative infinity. This time, what is your right-hand side doing? Positive infinity. And your asymptote is? It's still a vertical at x equals 0. And your y-intercept is still where? 1, 0. And now our concavity is what? It's up, and that's because our rate of change is increasing. So now we can say, yeah, it's less than 0. So it's
It's just gonna
so your rate of change is negative, but your y is decreasing on its domain. So at what the rate it is. Yeah. All right. So these rules are going to apply for when your x is greater than your base. I'm sorry, your b is greater than 0 but less than 1. On the other one, it's going to be greater than 1. When b is greater than 1, these are our attributes. So when b is greater than 1, we're going to have our concave down situation. When b is between 0 and 1, that's where we'll have our concave up situation. All right, so now we're going to look at a word problem. So we have our attributes down. If you're given a graph of an exponential function, do you feel comfortable analyzing it?
Yeah.
Do you feel comfortable identifying these 7 characteristics of the function? Yes? All right, cool. All right, let's dive into word problems because this is our area that we usually need to work on a little bit. Is this true? Okay. All right. So up first, it says, Suppose you invest 2,500 in an account that pays an annual interest rate of 6% compounded continuously. We know the balance in the account after T years can be found by the model A of T equals 2,500 e to the 0.06 t. Use the table of value for A of T to graph a logarithmic model that will display the account balance as the input with the year as the output. Okay, so the first thing we're going to do is it wants us to go from an exponential to a log. Okay, does anyone know how to do that?
So do we start with here? We rewrite the equation. Is it 2,500? Wait, so we're going from exponential.
We're going from exponential to log.
Okay, so you go. Let me see it.
You have to have this by itself, right?
Yes.
Ready? We're gonna work it out. You want to work it out?
Yeah.
All right, here we go. So first thing I'm going to do is I'm just going to let A of T be Y because that's extra equations. So our goal here is basically to get T out of the power. Okay, when you're going from an exponential log, your goal is to get the T out the power. All right. So the first thing we're going to do is separate it. So we have Y equals 2,500 e to the 0.06 t. What is the first thing I need to do to get the exponent by itself? Divide by 2. So now we have Y divided by 2,500 equals E to the 0.06 t. Okay? All right. We have to take the log, but E is special. It's ln. So remember with E, instead of, you don't use common log, you use natural log. So we're going to take the log of both sides. Agreed? I'm going to take the natural log of both sides. So the natural log of this side and the natural log of this side. When I take the natural log of the right side, what does it do to the E? It cancels it out and sets the exponent free. So now we're left with the natural log of Y over 2,500. ln is natural log, yeah. It's what the log you use when you have an E. Yeah, it's backwards. And we get,
Then we have to
what's the final thing?
divide.
Divide by 0.06. So now, do we have our inverse equation? Yes, we have our inverse equation.
Wait, why is it reversed? Did we never like switch the? She did, but without changing variables. Like she didn't change X and Y, but since we basically solved for X, we did the same as just doing.
Yeah, I just didn't switch. But you're gonna need to do it anyway, right? The reason why I didn't switch is because now your Y is your A of T, and you know that this is what you're solving for him out. So this is saying time given the amount, right? So if I have the time given the amount of money, I don't know why I made it a capital T. Oh, just go with it. Our equation is going to be the natural log of our amount, our A, over 2,500 divided by 0.06. If you don't want to write it as divided by 0.06, you could also write it as a fraction in the front. I am. It's an A, your amount. Okay, so now that you have this equation, could you do part B? I am. Okay, I'm gonna run to the bathroom while you do part B. Ready? All right, so on here it says estimate how many years before your 2,500 initial investment will double. So I'm looking for A equals what? I need my A to equal 5,000. So I can use the natural log equation we created, correct? To find that. So we have natural log of 5,000. I don't know why I did that. I even changed pins, guys. I don't know. Divided by 2,500 all over 0.6. 0.06. If you don't want to write 0.06, you could also write it as what? 6/100 is what this means, 0.06, 600ths, which could be 3/50ths, right? Okay. So once you plug this in, how long did it tell me? 11 and some change, right? So about 11.6 years, right? It's how long it would take us to double. So 11.55 or 11.6 years, however you choose to write it. All right, so we're going to complete the table and compare the data that we have. Okay, so when you are doing the table, you have, where's my table? Okay, I don't need it anyway. I didn't want it anyway. I didn't want a table. But when you did your table, did you notice that your X's and Y's switched? That's the goal. As long as you're recognizing that pattern. So for time of 0, where were we at? Okay, for time after 4 years, where are we at? Perfect. At 8 years, where are we at? 40, 40, and 19 cents. It's money, so you can do change, right? I'm just saying. At 12 years, where are we at? Keep the change. At 8 cents.
No, it's 1 cent.
Oh. And 1 cent. And then 15 years, where are we at?
And no change.
It was a penny.
Oh,
It was a penny. There was a penny. There was a penny left. There was a penny left. I want my penny. All right. How do we feel about log graphs using the given equations? 12 was 5,136 and 8 cents. Huh? 15 was 6,149 and a penny. That's your inverse. Your A comma T is your inverse. So if you're given this amount, how long will that take? So all you're doing is doing what with those values? Switching. All right. Are we ready for example 5? So example 5 is going to have us graph the natural log. And its inverse. That's what we're going to do. Yeah, mine don't have lines either. Okay, so we're gonna do natural log. Natural log, it's a decimal. So the only real value that you're gonna focus on is 0. So that's why there's no y values, because we're just gonna focus on the basic attributes of it. Okay. I'm gonna put in my asymptote because all log equations have a vertical asymptote at x equals 0. Also, all log functions are going to have an intercept at 1, 0. So all log functions have parent functions, I should say. So the parent function, ln x, has a vertical asymptote at x equals 0, an x-intercept at 1, 0. And it goes, and it's going to go. I tried. Thank you. I did my best. Okay. All right. Because of that, my analysis is going to be much different than a regular log function. No. What we are going to state a fact is that for natural log of x, the reason why this is a log is we're going to write it also in its log form. So in log form, natural log of x equals log base e of x. And e is going to be greater than 1. So it's going to have the same attributes as all log functions that are greater than 1. Does that make sense? All right, so putting that together really quick, our domain, what is it again? 0 to infinity. What's our range? All real numbers. what's next? Our limits. Yes, thank you. Our limit as x goes to positive infinity. What's happening? As x goes to positive infinity, what is your y doing? Going to positive infinity. The limit as x goes to 0, because it can't go anywhere else, right? What is your y doing? Is going to negative infinity. And because of these actions, what type of concavity do I have? It is concave down, down. Okay, and that's because my rate of change is decreasing. Bye. All right, how do you feel? Okay. Just want to, I just had to point out the relation between log and natural log. Good luck. Are we comfortable with understanding natural log works the same?
Yeah.
Oh, can someone, I forgot, approximate value of E. E is just a 2.3 and something. So you know what E is, just like pi. 2.7183, right? Yeah. And that's why I said that is greater than 1. Okay, E and pi are just numbers, irrational numbers, but nonetheless, they are numbers. Okay. Okay, so your, what do you call it thing you did today? Do now. Goal was to get you to remember transformational rules, right? Yes. So with transformation rules in mind, hey, did you need me? It's tomorrow. We don't have it until tomorrow. Okay, if you could give me a second. All right. So we have our transformational rules, and it's wanting you to apply those transformations to this function. Okay, that's option number 1. For graphing purposes, it's not that bad. And then we're gonna find the inverse. Okay, so for this graph, what am I doing? How am I shifting? Vertically stretched by 2. So I'm vertically stretching by 2. That means for all of my y values of my parent functions, they are being multiplied by 2. Agree? And then I'm doing x is doing what? They're liars, so we're going to the left 1 unit. So we're taking all of our points, shifting them left, and then stretching them. Does that make sense? All right, so I'm gonna mark out my parent function points just so you can see where we're at. So the parent function for log base 2, we're at 1, 0, 2, 1, 4, 2, and 8, 3. And we're gonna apply these transformations to these 4 points. Does that make sense? We're going left and we're stretching by 2 by multiplying your y's by 2. No, that means that you're taking your y values and multiplying it by 2. So you're going to go left and then do your y. So 0 is going to stay the same. All right, I'll give you a moment to try it, and then we're going to check and see where you're at. Okay, so quickly move these 4 points.
So you put it out. So you zero times two. One times two is two. Yeah. You're welcome. Yes.
Are we ready? Okay, so where is our new home for 1, 0? It's now at negative 1, 0. Is that what you said? At 0? At 0, 0? Oh, they just said 2, 0. I heard. All right, we're now at, where does 2, 1 go? We're now at 1, 2. Go. Where is 4, 2? What'd you say for 4, 2?
That was 7, 14.
For 4, 2?
Oh, 36. We just did it. That's
2 times 2 is 4.
Oh, we did the X's. We did that.
I was like, wait, that wasn't right. All right, and then I went left 1. And then 2 times 2 is 4. Right? So 7, I go left 1. And 3 times 2 is 6. So now I shifted and I stretch. So now that also caused my asymptote to move. So instead of my asymptote being at 0, my asymptote is now where? At x equals negative 1. Okay, so this is my f of x, and I can describe the attributes. Now it wants us to find the inverse algebraically and then graph the inverse. Well, I can easily graph the inverse, right? But we're going, because in order to graph the inverse, all I'm doing is taking the values and switching them. So instead of 0, 0 is still going to be where? 0, 0. 1, 2 becomes what? 2, 1. Because it says graph the inverse. What does your inverse mean to do? You're just doing what with your inverse?
So like flipping it.
Yeah. Huh? Because everything was shuffled 1 unit to the, so my asymptote also has to shuffle. All right, so we're here. Where are we at? So if I'm at 3, 4, I'm now at 4, 3. I'm at 7, 6. Now I'm at 6, 7. We're doing our inverses. Am I doing something wrong? Or is it not clicking? Okay. And instead of a vertical, it says graph the inverse. And I said this will be faster, so we're doing the graph. We're graphing it first, and then we'll do it algebraically. Yes. We're doing the inverse of what we graphed. No, of the function of f of x. F of x equals 2 log base 2 of x plus 1. We graphed it. Check. We're now doing the inverse because I said it would be faster for us to just go ahead and graph the inverse, and then we're going to do it algebraically. Got to lock in, guys. All right. So now, instead of having a vertical asymptote at x equals -1, we're now gonna, what's the inverse of vertical? Horizontal. So we're gonna have a horizontal asymptote at y equals -1. So here goes my inverse function. Okay. Now we're going to do it algebraically. So algebraically, I want you to find the inverse. Okay. Essentially, when you're finding the inverse, if you don't want to switch x and y, you're just getting x by itself, right? That's what the inverse is. But traditionally, we say switch your x and your y. The reason being is because you're used to solving for y. You're used to getting y by itself. So log base 2 of y plus 1. Okay. My goal is to get this free, y free. What's the first thing I need to do? I'm going to divide by 2. I can't do anything until I divide by 2. So I divide both sides by 2, and we're left with x over 2 equals the log base 2 of y plus 1. Okay? How can I cancel out a log? It's exponential. You do. You raise it to the second power. So it's to the 2. Okay? That's because if you raise this to the second, the log and the base are the same, and they're going to do what? Cancel each other out. So we're left with 2 to the x halves equals y plus 1. So therefore, my inverse is -1. Okay, so we're going to talk about domain and range here. What's the domain? What's the domain for my original function? 0 to 0 or -1? -1 to infinity. What's the range? All real numbers. What happens to my limit as f of x, as x goes to infinity? What's happening to y? Positive infinity. What's happening to f of x as x goes to negative infinity? It's going to negative infinity. Asymptotes. We have a vertical at x equal -1. And our intercept now is where? 0, 0. Did our concavity change? Nope, we are still down. And that's because our rate of change is positive, but it's decreasing. Guess I should practice writing it. Rate of change. If I write greater than 0, is that fine? Does that, y'all know that means positive?
Wait, what is it? Down? I'm just gonna.
Is she joking? Or is she serious? Okay. Well, then you write positive. Oh, and decreasing. All right. On the other side, what's happening? What's my domain on this side? All real numbers. Good job. Negative infinity to positive infinity. What's my range? -1 to infinity. Does it make sense that the domain and range switch places? Yes, because except this one has a different limit. It has an actual limit, right? The limits are gonna, sometimes they will, but there's not guaranteed, especially if there's an asymptote involved. All right, so limit as f of x as x goes to positive infinity is what? So we're looking at the purple. It's also doing what? It's increasing. Okay. However, what happens as I'm going to the left on my axis? It's approaching what? -1. I may not ever equal it, but I can approach it, right? I'm gonna get as close as I can. Okay, and now we have a what? We have a horizontal asymptote at y equals -1. My y-intercept and x-intercept is still at the origin, but this time, what are we? We're concaved up. Our rate of change is still positive. It's just now increasing. So our rate of change is positive and increasing, which is why it's up. Does that make sense? All right. How do we feel about part 1?
So